1. All right, I like example 18 because I'm giving you, it's kind of like 2 of these we can do and 1 of them we can't. And we got to figure out which ones we can do and why we can't do the 3rd one. So if you kind of scan them real quickly, it looks like the only difference among the 3 is the power of x in the numerator. Yeah. So in each of them, we can pull the 3 out front. He's like, not even really there. I could have thrown any number there. So let's see if we could do the first one here. So again, if you want, kind of as your method of housekeeping, bring the 3 out front. You've got a factor in the bottom, so it's a division, it's quotient. You could bring it to the top, and that forces you to put it into a fractional exponent, -1/2, yeah? And so now you have this outside function, because it's a product of 2 variable functions. The outside function is this, and instead of doing formal U substitution, you just check. What's the derivative of that? You compare it, and it's -4x cubed. And you're like, hey, that's where the x cubed came from. We're just off by a -4, but we know we have it, right? So the 3 goes along for the ride. If we're off by a -4, we put a correction of -1/4. And as soon as you make your correction, now you move on to the rule of integration, right? Blob to the -1/2 is the power rule. So leave a space, add 1 to -1/2, and you get a half. And now we multiply by the reciprocal of a half, which is 2. And then plus c. And of course, we don't walk away there, right? It's still the same inside function. That's kind of the little mistake I made upside down earlier. It's still the same inside function. Okay, it doesn't turn into just x. And then you have your 3 coefficients in the front. You don't always get all 3, but here we have all 3, right? You got your rider, you got your correction, and then you got your rule coefficient. So clean that one up if you want, but I think the essence of that is captured in there, right? Comments, questions on that one? We had a 4. Sometimes you could check, and you probably figured this out on your own, that you don't need to physically rewrite that in the top to the -1/2 to like check. You could just say, oh, if I were, 5 minus x to the 4th would be the inside function, and its derivative is -4x cubed, and you're like, yeah, it's going to work. So now I'll bring it to the top so that I don't mess up the power rule, right? So there's little, evolved strategies. And so like if you're looking at this one, you could say, okay, just like we did before, 5 minus x to the 4th would be the inside function, but its derivative is 4x cubed. And you're like, uh-oh, I'm off by an x, right? And you can't be off by a variable. You can only be off by a constant multiple. So this one is obviously not going to be done the way we just did A. It's not going to be a power rule, right? So what else do we have at our disposal? Do we have any techniques besides 3 get out front? Well, remember, arc secant, perhaps, right? Very good. If it's going to be any inverse trig, it's got to be arc. Wait, did you say secant or sine? I'm sorry. By the time it hit me like 3 rows back here, I heard sine, but then I heard secant after my brain processed sine. Yeah, it would be arc sine if it's going to be anything, because you have number minus function. That would be a squared, and this would be u squared, right? Number minus function is like 1 minus x squared. So if a squared is 5, a would be the square root of 5. And if u squared is x to the 4th, u would be what? What's the square root of x to the 4th? X squared. Now, remember, we got to check whatever it is we're calling u, in this case, x squared, its derivative has to be the other factor or only off by a constant. What's the derivative of x squared? 2x to the 1st. Ay, caramba. We're off by an x again, but this time on the other side. We're not generating the x that we need. We're an x short instead of an x heavy. So, man, I don't think we can't do this one. Cannot do this one. And I'm going to put ... yet. Right? Maybe there's a way later on. Maybe in an advanced method. Maybe, that's right. Season 2 would be after the AP exam. If we learn like trig substitution, there might be a way to do it. All right, now look at this one. On this one, you're like, whoa, this is kind of what I just did this, right? Yeah, so I got my a to be the square root of 5. U was x squared. Look, this 3, you're already in the answer, okay? Yeah, you're already in the answer. The derivative of x squared is 2x, so now I'm off by a 2. So I have a correction of a half. Okay. And so now I know that I'm ready to do the rule of integration once I make my correction of a 2. And this one is arc what, Mason?
Sine.
Arc sine. Good. Now, does arc sine, here's the question, does arc sine have a 1 over a built into the rule? No. Very good. Very confidently. No. No. Yeah, that's right. It doesn't just flow off the tongue, right? No, you have to kind of get that tongue in there. No, no, no. And sometimes it gets stuck. No, 1 over a is not there for arc sine. It's the only one. So we go straight to arc or inverse sine of u over a, x squared over the square root of 5, and then plus c. And there it is. Okay. Comments, questions on that one? All right. Time for more strategies. Example 19. Kind of the same idea, slightly different instructions. Find each of the following, comma, if possible. Okay. I'm up for the challenge. Are y'all? Yeah. Now notice these all have the same numerator. The only difference is the denominator is a trinomial polynomial, right? The quadratic. And the constant is different. They're all even in the same room with us, like mentally. No, get there. Come on in, because it's distracting. And now it's on video, right? I mean, it looked interesting. Maybe during sea lunch or advisory. All right. Yeah, I know. There's a lot of energy in here. I don't want to have to hobble y'all. That's what you do to a horse if you're sleeping out in the wilderness and you don't want it to leave during the night. You just hobble it. They can still get the water, but they can't run off. 9, 10, 8. 9, 10, 8. Well, let's see. Let's just see. If I were to do, let's see, if we go through kind of our housekeeping, right? 3 to the front, right? And then Ethan, the whole denominator would come to the top. And this is a good thing to do because it forces you to put it in parentheses. Sometimes the hardest function to see is the one that's something to the first, because we really don't need parentheses. Now, the person that doesn't know anything past this would just go straight to natural log of the absolute value of that, right? But not us, because we have to always check whether we have an actual function like blob to the negative first, or if we have something like whoa, or if we have something like g to the 1/2 x, right? Or g prime, right? Whenever we have an inside function, we always got to check what's the derivative of this. Well, it's 2x plus 6. Do we have a 2x plus 6 or 1x plus 3 or any multiple of that out front? No, we would need a 2-term dude out there that's a multiple of 2x plus 6, and we don't have it. So it's not going to be a natural log. Yeah. Not going to be a natural log. So what strategies have we already had? Well, we could split up the numerator. Doesn't really work here because it's just one term, right? Inverse trig, right? Oh man, inverse trig would work nicely if the 6x were not there, right? 6x, you go away. All right, now it could be arc what? Arc tangent, right? Maybe it's our, so dang, wait. Okay, well, let's see. Factor it. Is that what y'all said? Yeah. When in doubt, F it, right? Yeah, when in doubt, guess and check. Factor it. Let's try to factor it. Bring the 3 out front. This factors into x plus 3 quantity. Yeah, x plus 3 quantity squared, right? Oh boy. Now you reset your mental flow chart, right? Now it's like a brand new problem. What's up, problem, right? And now you might bring that to the top. And it's to the negative 2th power dx. And now you have an outside function blob to the negative 2, and your blob is x plus 3. And now you check, what's the derivative of x plus 3? 1. Are we off by anything? Nada, right? So we've got it now. So 3 goes along for the ride, and it's a power rule. So blob to the negative 2nd becomes blob to the negative 1st. Either divide by -1, or in this case, multiply by -1, which is its own reciprocal, plus c, right? And we're done right there. Yeah, right? No, I always put the blob in last, right? There's the blob. All right, so if you clean that up now, -3 over x plus 3 plus c. Yeah, there you go. So there's the strategy right there. Factor it. Factoring worked in this case. And it turned into a really nice linear inside function. When your inside function is linear of the form mx plus b, you're only going to be off ever at most by a constant multiple. So it's going to work, right? Like sine of 5x, the inside function is 5x, you're off by 5. Keep those streaks alive there. Yeah, you got to keep that streak alive. Okay. Letter B. Hey, the fact that it was a 9 here, now it's a 10, right? I mean, really, come on. Like, what difference could like +1 make? I mean, it's probably going to be the same answer, just like +1, right? Like plus x plus, right? Because that's how math works. Well, I don't know. I mean, it's not going to work the same way. If I put this to the first, it's still not a natural log because the derivative of that is 2x plus 6. And again, there's no two-term linear factor up there. So that's not going to work. Can we factor this one? Well, let's see. 3, you go out front. Okay. And let's see. This one's not a perfect square trinomial. So here we go. Factors of 10 that add up to 6. 5 and 1. No. 10 and 1. No. 20 and a half. No. 3 and 3 and 4. No, it's not looking good. It's not looking good. This one does not factor. Crapola. Here's the strategy. And this one's important because this one is on the AP exam. Okay. There's a lot of strategies that I teach you that aren't on the AP exam. This one is. Okay. We can actually turn it into something like this. We can turn something that's not a perfect square trinomial into a perfect square trinomial by completing the square. Y'all remember completing the square? Okay, let's go off to the side on our workbench. Completing the square. Complete the square. Completing the square is really just adding 0, right? We multiply by clever forms of 1 all the freaking time. Completing the square is essentially adding a clever form of 0. So let's take our polynomial over here. X squared plus 6x plus 10. And you're like, 10, you know what? You were not very helpful at all. If you were a 9, it'd be really helpful. Now, if you realize that, you could say, well, I can call 10 9 plus 1, couldn't I? You could split it up. But in general, you might not recognize that. So here's how you probably learned it in Algebra 2. If you do it on an equation, you can add the same number to both sides to keep the equation balanced. But we're doing it on an expression. So what we're going to do is we're going to add a clever form of 0. So the first thing you have to do is make sure the coefficient of x squared is 1. And if it's not, you got to factor it out of your quadratic and linear term. All right, now we're going to say plus something, and then plus 10. Yeah, you're sent to the back of the line, right? You're just worthless. All right. And then here's what we do. We decide what to add by taking half of the linear coefficient, and then we square that number. Half, then square. Y'all might remember that, right? Half, then square. What's half of 6? 3. So we get 3 squared here, which is 9. I'll just call it 9. And because I added 9, I need to make sure it's a 0 pair. So now I'm going to add the opposite of 9, which is -9. Okay. So some people put like a blank plus minus. I don't like that. I just put plus plus, and I have to make sure that's 0. Now, if you add those together right away, 9 minus 9 is 0, and you're back to where you started, right? And that's a good way to check. But now the associative property of addition comes into play. Watch. Kaboom, kaboom, right? Shaboom, shaboom. That's what I meant. Right. And now, of course, the first part factors just like we did on the previous problem. It's x plus 3 squared. And then these two guys, what wasn't helpful in the beginning and the leftover, they could say, hey, you doing anything? Nah. You wanna get together? Sure. -9 plus 10, and they become 1. Ooh. And they become 1. Yeah, it's not quite opposites attract to become 1. They're close to opposites. So let's go ahead and import that over here now. The denominator is the quantity x plus 3 squared, but I have this residual 1. I have the 1 there. Ah, crap. Well, if that plus 1 weren't there, it would be exactly the same as the other problem. So does this really help me? Well, now if I bring the whole thing to the top, it's the whole quantity to the first power. And is the derivative of this in the top? Well, no, not really, because the derivative of the first piece would be the chain rule, right? 2 times x plus 3 to the first. No, then so that doesn't work. So here's what this happens. Whenever you do a completing the square, it usually turns into an inverse trig. Okay. What we're doing is we're completing the square to turn it into an inverse trig problem. All right. Now, it doesn't have a radical, right? So if it's an inverse trig, it's got to be arctangent. Well, look, this is u squared and this is a squared. We don't have to limit u to a single term, right? So let's see, what would u be? What's the square root of x plus 3? X plus 3. What is u? And in this case, what is a? 1. Now, don't forget, we got to check. What's the derivative of x plus 3? 1. So there's no correction to make. So we got it. We got it. 3 goes along for the ride. 3 goes along for the ride. There's no correction to make because derivative of u is just 1. Now, does arctangent have a 1 over a in front of it? It does. So it's 1 over 1. Oh, if you forget it, you get lucky, right? But I'm going to put it because I didn't forget it, it did. And then it's arc or inverse tangent. I'll do inverse here of u over a. So x plus 3 over 1 plus c. And free response, I'm just walking away there. I'm not simplifying. AP reader's going to see that and they're like, dang, they were taught well. Look at that. Dang. Okay. And then, of course, on a multiple choice, that won't be there. So it's 3 inverse or arctangent of just the quantity x plus 3 plus c. Nice. And if you want, you could verify that that's right by taking the derivative. Yeah. Yeah. If we had time, but we don't have time. Okay. Plus, at this point, we know it's right because we're getting awesomer and awesomer the more we practice and practicer. I don't know if that works. Okay. So it worked. It worked for a 9. It worked beautifully for a 9, just a power rule. And it worked for a 10 because we completed the square. So will it work for an 8? Maybe, I don't know. Well, let's see. 3, you come out front. Does the bottom factor? I think, yeah, it does factor, right? 4 and 2. And they're both positive. Yay. This factored into the product of 2 linear factors. Okay. So does that help me though with the, I can't, if I split them, can I? Hey, can I do this? Can I say it's 1 over x plus 4 dx times the integral of 1 over x plus 2 dx? No, you can't. There's no product rule. There's no product rule. There's no product rule. It can't do that. So right now we're stuck. Okay. We are going to learn a way to do this later on called partial fraction decomposition by the Oliver Heaviside cover up method. Or as I call the Peter. Yeah. Yeah, we're going to learn that later. It's an advanced, it's a BC only topic. Partial fraction decomposition by the Oliver Heaviside cover up method. I'm going to spell cover up with one word because I got adolescents in the room. There we go. All right, Bendeley. Thank you. Thank you. All right. Okay. But right now we can't do it. What about completing the square though? Will completing the square work? Let's try it. That's 1 over. Let's see. Let's see if we can complete the square a little bit easier. We want this to be a 9, don't we? So can we just call 8 9 minus 1? Okay. So that might be, and you could do the same thing, right? You could say, okay, half of 6 is 3, 3 squared is 9. So I'll add 9 and then I'll subtract 9, and negative 9 plus 8 is negative 1. So however you want to do it, we can now associate these together. Notice I'm completing the square in the problem this time. So I got to bring down all the other pieces. So this is x plus 3 squared minus 1. Ah. Is that arctangent again? Why not? There you go. The minus messes it up. All right. Arctangent has to be both positive terms. Function squared plus function squared. no radical. It can't be an arc secant because there's no radical around it. You can't manufacture the radical, right? So yeah, this one we can't do it this way. We can only do it by the partial fraction decomposition by the Oliver Heaviside cover-up method. You want a preview of what that looks like? All right, let me show you what that's going to look like. So here's it. This might be the only lesson that we need on this whole thing. Okay, like I could skip that whole section later on, but if I do, then I don't get to talk about the spoon break. Yeah. All right. So the method that we're going to do is called partial fraction decomposition, and the method that we're going to use was a method that was made famous by Oliver Heaviside, who incidentally was a very, very thin mathematician who invented the spoon break. You know what that is. But here's what it is. If you could factor the denominator into non-repeating linear factors. Non-repeating means they're both to the first power. So if one of those were squared, you'd have to do partial fraction decomposition in a little bit different manner. But if they're both linear factors of the form mx plus b, and they're both to the first power, then you can quickly decompose this, we say, into two partial fractions. That's the sum of the difference of two fractions by what's called the cover-up method. All right. So here's what you do. You factor it, and then you're going to set yourself up like this. We're going to decompose it into two partial fractions. So one of them is going to be something x plus 4, all right, like that. And the other one's going to be x plus 2. Now, how do we decide what the numerators are? That's the key. Because what happens is I need to be able to get a 1 when I cross multiply and do all that, eat that stuff to get a common denominator. But here's all I have to do. The numerator of this one is going to be found simply by asking yourself, what value makes x plus 4 0? In other words, what's the root of x plus 4? Well, it's x equals -4, right? Okay, so what happens now is you take the root, -4, and you go up to the line above where it's still fully intact, and you cover up the x plus 4 factor. That's why it's called the cover-up method. And now you plug that -4 in to everything that's left. What's left? 1 over -4 plus 2. What's -4 plus 2? -2. So what do we get? 1 over -2, or -1/2. That number that you get, is the new coefficient of that fraction. Okay? It's called the cover-up method. And watch, we'll do it on the next one as well. Okay? What value makes x plus 2 0 when you plug it in for x? -2. So you go up above, and now you cover up that factor, and you plug a -2 into what's left. You get 1 over 2, positive 1 over 2. So positive 1 over 2 is the new coefficient. All right. Now, if you want to verify that that gives you a 1, you could get a common denominator or do your crisscross applesauce. You'll see that the x's cancel and you're left with the 1 on the top. That's an easy way to do partial fraction decomposition. That's what that's called. We decompose that into two partial fractions that, when added together, gives you the single fraction above. Okay. Now, why is that helpful? Because look what we could do now. I can factor out the 1/2 from both of them and put it out front with the 3. So this becomes 3/2 the integral of, and I'm going to put the x plus 2 first because I don't like to lead with the negative. And the second one will be -1 over x plus 4. Okay. Now, while there isn't a product rule, take the integral of one times the integral of the other, there is a sum and difference rule, right? I could take the integral of term down the line. So here's what it becomes. 3/2 goes along for the ride. And then look, what is the antiderivative of 1 over x plus 2? Well, x plus 2 is in the denominator to the first power. Again, that's kind of hard to see, but if you brought it to the top, right, you'd see that it was to the negative first. And what's inside? X plus 2. What's the derivative of x plus 2? 1. Are we off by anything? No. So when your inside function is in the bottom to the first or in the top to the negative first, what's the rule of integration? Natural log. Yeah. Boom. Minus kind of the second verse to the same song, right? Second song to the same verse. I'd like to hear that. Again, blob to the first and the bottom. What's the derivative of x plus 4? 1. We're not off by anything. So this is going to be minus the natural log of the absolute value of x plus 4. Close that up, plus c. And if you wanted to distribute the 3/2, you could. The 1/2 came from the numerator up here. They both had a 1/2. So I just factored the 1/2 out front. And then I flipped the terms around because I don't like the negative leading in the front. So I just did that. So that's called, we'll do some more later on, but that's called partial fraction decomposition. And the only thing that y'all are responsible for on the BC exam is when it does factor into non-repeating linear factors. Okay. So there you go. There's your BC only topic of the day. Yeah. All right. Don't leak that information to AB kids, right? Y'all are exclusive now. Okay. So yeah, we could actually do all three of those, right? And it's very subtle difference, a 9, 10, and an 8. One is just a simple power rule. One we complete the square, it's inverse tangent, and the other one turned into funky logs, right? But possible. All right. Fantastic. I like that. I like that. How are we doing on time? Plenty? Yeah. 30 minutes? Oh, sweet. All right. So let's take a look at that in example 20. This is kind of an application. 31. Yeah. Find the area of the region. Now, as soon as you hear that or see that area of the region, you're like, area. Area has to be positive. Area has to be positive. Who's in charge of making it positive? You is. I am, right? Me is, right? Myself is. That's how most people speak these days. Ugh. That's, oh, that hurts just to say a joke about it. All right. Bounded by this graph. So now you're going to be given functions that define a region, kind of like the borders of Ukraine, right? F of x is 1 over the square root of 3x minus x squared. The x-axis and the two vertical lines. These are vertical lines. X equals 3/2 and x equals 9/4. Verify on your calculator. Well, here's what the deal is. Is this function ever negative over its domain? No. The top is always +1, and the bottom, anything that comes out of it is going to be positive square root. So this is always a positive over a positive, which is positive. So I know I don't know what the graph looks like exactly, but I do know that the graph lives above the x-axis, right? F of x is already above the x-axis. So when I'm sketching it, just for reference, which I will, all right, here's what it looks like, right? No. Now the domain's not going to be all real numbers because 3x minus x squared doesn't have a domain of all real numbers, but there's the curve f of x, right? You like it? And then the x-axis, that's this, right? I know where that's at. That's that. And then the vertical lines, x equals 3/2. I'll draw that here. And x equals 9/4. Now I can assume that those are going to be on the domain. So there it is. So I want the area is already taken care of, right? If I just integrate from left to right, I should have it. So let's set up an integral. So I'm going to say the area, because I know it will be, it's the integral from left to right, from 3/2 to 9/4 of my function. Now, because I have to do it by hand before I verify in the calculator, because this question could show up on either type. I'm going to put the actual expression in there. If it were just a calculator question, I would just nuke it with absolute values, remember, right? And just integrate from left to right. Okay, so now I have to find the antiderivative so I can use the fundamental theorem of calculus. This is your inside function. If you were to bring it to the top and write it to the -1/2 power, just to check what its derivative is, you could, but you could check it in the denominator. What's the derivative of 3x minus x squared? Oh, it's 3 minus 2x. Do we have a 3 minus 2x factor? No, so it's not going to be a power rule. Criminy. So already kind of at our, method of last resort. It has a radical, so inverse trig, right? It has a radical, so it can't be arctangent. It's either arcsine or arcsecant. Now, this one isn't function minus number or number minus function, right? This one is function minus function. If I pulled the x out, let's do that off to the side, I would have the square root of x times 3 minus x. Now, that's not going to help either, because if I did write that, that would be x to the 1/2 and 3 minus x to the 1/2. I would not be able to decompose that because those are not linear factors, right? They're repeating. They're all to the 1/2 power. So the partial fraction decomposition by the Oliver Heaviside cover-up method would not work here. So that doesn't work, but that's good to know you can factor out an x. It's something to do. So what else could we do here? Well, if you're expected to know how to do it, and maybe it's an arcsecant or an arcsine. I wish it were just a number minus a quantity squared, or quantity squared minus a number. So is there any way to make 3x minus x squared a perfect square? Can we complete the square on it? Yes, we can. All right, let's go ahead and complete the square. Complete the square. And I'm going to do it off to the side because I don't want to have to do it in the problem and write all the notation. So 3x minus x squared. All right, so here's what we do. First of all, I'm going to put the x squared term first, right? That's the way we like to see it. And completing the square only works if the leading coefficient is 1. So whatever it is, it's just a negative here. I got to factor it out. So I'll factor out a -1, and I'm writing it. It's positive x squared minus 3x. Now, here's the deal. I have to complete the square inside the parentheses now. If you ever complete the square by factor something out, you're going to add something inside. Okay, because that's what needs to be the perfect square trinomial. Then you want to close the parentheses and put plus something else. Now, here's the deal. There's not a constant there like there was before, like an 8. There's a 0 there. So let's just proceed. We'll complete the square now. What's half of -3? -3/2, right? And then we square it, and we get positive 9/4. Oh, what a beautiful number. Okay. Now, here's the deal that you got to be careful. If you were to expand that back out, I didn't really just add a positive 9/4, did I? If you distribute, I really just added a negative 9/4, yes? So now I need to make sure that when I redistribute, I have the opposite of that number sitting outside. What's the opposite of negative 9/4? Positive 9/4, okay? Now, you could verify right here. If you distributed the -1 and combined like terms, you would end up with just the purple part above, yes? All right, now let's go ahead and factor that. That's -1 times quantity squared plus 9/4. Well, the quantity, let's see, it's going to be an x, and then all you have to do to figure out what the other term is, it's going to be half that middle term. It's this guy right here. It's x minus 3/2 quantity squared every time. And you can square, multiply, double, square to figure that out. It does work. Square, multiply, and double. -3/2 times 2 is -3. Square the last, you get positive 9/4. All right, so I'm going to bring that back into my problem. And notice I did that off to the right-hand side. You never want to interrupt the flow of the problem with bench work, okay? Your bench work is located off to the side. All right, so when I rewrite that, I end up with this. I get the integral from 3/2 to 9/4 of 1/, and I'm going to switch these around because I told you I don't like to lead with the negative. So I'm going to write that as the square root of 9/4 minus x minus 3/2 squared dx. Everyone okay with that? We factored it. Yeah, it's a perfect square trinomial here, and we factored it. So remember, you can verify off to the side, x minus 3/2, x minus 3/2, you know, first, outer, inner, last. You get x squared, and then you get minus 3/2 x, minus 3/2 x, minus 3/2 x, and then the last is positive 9/4, and then these cancel, these double, right? The middle's double. There's 2 of them, so it just becomes 3x plus 9/4. So whenever you complete the square, it's always going to be x, and then whatever half the middle term is, quantity squared. All right, so this one is kind of gross, but it is completing the square. If you have to complete the square on the AP exam, it's probably going to be closer to what we did up here on part C, okay? I just want to show you that there are levels of fun to be had here. This one is shaping up now to be an arc what? I have a number minus a function squared. Arc Starts with an S. Arc sine. Number minus one. So that's a squared, and this is u squared. So, and I do write this underneath the flow of the problem. I say don't do that, but this is kind of the exception for me. So a equals 3/2, right? And u equals x minus 3/2. And now we check, right? Don't forget this part. What's the derivative of u, or your derivative? The derivative of x minus 3/2 is 1. Are we off by anything? Nope. So we go straight to the antiderivative. There's no correction. There's no rider. Is there a 1 over a in front? Nope. So this one is just arc sine of u over a. So it's x minus 3/2 all over 3/2. Whoa, no plus c needed, because now we're evaluating it from 3/2 to 9/4. Diggity donut, this one is fun. Now, I don't like that complex fraction. Do y'all? Ben delay? Don't, yeah, double jeopardy. No double jeopardy on your tribunal, but right, that was good. Let's state change flip here. I want to clean this up. Arc sine of state change flip. So dividing by 3/2 is the same as multiplying by 2/3. Yeah, don't distract Ben delay. Yeah, because it's infectious. All right, now let's distribute. Let's distribute. Or do you want to distribute? No? We can. It's up to you. I probably would. You get 2/3 x minus 1, right? A lot of algebra here, huh? Yeah. And now we've got it down to a point where we can use the fundamental theorem of calculus. Ethan had an epiphany. It's good. And it's good. He's a spectator here, right? He's injured, so he can't participate by writing it down himself. He has to sit it out and just be a spectator, right? Because everyone knows math is the spectator sport. Come on, Ethan, is your iPad dead? Okay, come on, stay on track here.
Sponges can't write that.
SpongeBob SquarePants can.
He can't. He's asleep. I'm not asleep. I literally have the math.
Thank you, Ben delay. Thank you, Ben delay. Yes.
So for we don't do a plus C, but is it because of the area or is it?
We don't do a plus C, or we don't need a plus C, simply because it's a definite integral. It doesn't matter if it's an area or just a net accumulation. If we did have a plus C, when I plug in the top minus plug in the bottom, we're always going to get C minus C, and it's the same C. No, a definite integral doesn't always give us area. It always gives us net accumulation. But anytime we have a definite integral, whether it represents area or just net accumulation in general, you don't need the plus C. Okay. All right. You can certainly have it, and you'll see that it will cancel out. All right. Let's go ahead and plug in now. Plug in the top, right? So we get arc sine of, well, 2/3 times 9/4 minus 1 minus, plug in the bottom, arc sine of 2/3 times 3/2 minus 1. On a free response, are we doing anything else besides this? No. But let's keep going. Arc sine for multiple choice. All right, free response, we're stopping right there. All right, multiple choice, we keep on keeping on. So does this simplify? Well, yeah, I think it does. Watch. 2 goes in itself once, goes into 4 twice, and then 3 goes in itself once, goes into here 3. So this is arc sine of 3/2 minus 1 minus arc sine of 0. Yeah. Crap. Well, new column. Yum. Yeah, it's because it's 1 minus 1. 1 minus 1. Now, I just have one more line before I can actually use the unit circle inverse. 3/2 minus 1 is 1/2 minus arc sine of 0. Okay, now it's not unit circle time, it's time circle unit, because this is where we use the unit circle in reverse, right? Arc sine of 1/2. The way we answer that is sine of what angle is 1/2? Pi over 6. Excellent. And we don't choose 5 pi 6, even though sine of 5 pi 6 is 1/2, because it's outside the principal value range, right? Always go for the quadrant 1 angle if you can. And then arc sine of 0, we say sine of what angle is 0? 0, yeah. So this comes out to be pi 6. So the area ends up being a little bit more than a half, right? Okay. So that was kind of fun, kind of. That was a pretty hefty completing the square problem. Probably a step outside of the AP curriculum, but it is completing the square, and it does review arc sine, and it does review definite integration. Now let's check it on the calculator, Ethan. If this is strictly a calculator problem, then here's all we're doing. We're saying the area is the integral from 3/2 to 9/4 of the absolute value of f of x dx. That's how we set it up. We put the absolute values, which nukes it. We don't even care if it's already positive. No harm, no foul if it's already positive. And we write f of x because that's its name. It saves a little bit of time. So this would give you a check for the setup. And now we would go to the calculator. And I guess I'll pull mine up here. It hasn't been used all weekend long. Let's see if the ROM needs reloading. Oh, I'm sure it does. Yeah, you can go ahead and figure out what the answer is. If you want to grab a calculator to go with the keystrokes, help yourself. I like using this online one because I don't have to get up, right? All right, so here we go. From the home screen, math 9, remember? We're going from 3 divided by 2 up, oops, I forgot the 2. Up to 9 divided by 4. And I don't have it typed into Y1 because it's like a one-shot multiple choice disposable problem. So I'll just type it in as horizontal division line, alpha Y equals, or for y'all can hit what, alpha X, I believe, maybe. Oh, yeah. How do we get out? I need those first. Yeah, math number 1. Math number 1. Well, I'm saying, like, if it's a calculator question, we don't even care if it goes negative or not, right? We're just being careful, and we're not taking the time to decide if it is or not. Now, my calculator is on super fast ROM mode, so I can't scroll to the right without going past the NUM. So here's where else you can get it, right? Alpha window, number 1. Not as good of a cheer, though, right? And then alpha Y equals for the horizontal division bar, 1 divided by the square root of 3x minus x squared. Okay, 3x minus x squared. Oops, what did I do? It's not letting me square it. Uh-oh. It did? Oh, man. Yeah. Oh, okay. It's giving me like this weird symbol. A little box? Oh, yeah. I don't know why that, but, huh. Okay. So let's try this. If it, I know it's supposed to work. I don't know why it didn't let me type it into the home screen, and y'all did the same. So let's just type it into Y1, right? We have another way. We're not going to let the Russians take our city. We got another way. All right, so we got that. Now we'll go back to the home screen, math 9, from 3/2 to 9/4 of. Now we'll do the absolute value. Alpha window 1, alpha trace number 1. Take that calculator, and you get 0.523. All right, so then we just put it underneath here, 0.523 or 524. Now let's see, what is pi divided by 3? Or it was 6, right? Is that what we got by hand, pi 6? Ah, it's the same. See? So I don't know why I didn't let's type it in. I've never seen that before. Never happened before. First time for everything, right? On the end of February, last day of February, go figure. Like the Friday of the month and things go wrong. But Sisu, right? You just go to Y equals. So it's the same, right? With the calculator again, super easy. Super easy. By hand, super fun. Super fun. Okay. Completing the square is the strategy. We're not done with strategies now. Let's look at example 21. Look at example 21. You have a quotient, right? If you were to rewrite it using kind of like your standard protocol now, bring the factor from the bottom to the top, it's now to the negative first. Okay. If you actually wrote it, that's fine. Or if you're doing it in your head at this point before you write it, because it doesn't always work. But now you're like, okay, the more interesting factor is the blob to the negative first. So that could be your outside function, which means it would be a natural log rule of integration. But the inside function is a quadratic, x squared plus 1, and its derivative is only 2x. And so now you're like, oh, crap. I'm off by, I don't get those other two terms. What gives? Well, that's not going to work, okay? So not going to work. So what you could do, and here's the strategy, you could either do in this case, which doesn't always work, you could split up the terms on the top. I don't know why it's not letting me. He is fighting back. Okay. I think because I grabbed part of the image. Yeah. All right. I could try to split it up. If you notice, I could take the x squared plus 1 and put it over x squared plus 1 plus x over x squared plus 1. But that takes a little bit of insight. So here's the new strategy, okay? When the degree of the numerator is greater than or equal to the degree of the denominator, guess what we're going to do? Use, lean in and listen. What is this line saying? Divide me. Divide me. Division. We're going to do long division. Okay. I guess I should say long division as opposed to synthetic. Hello. I'll get that later. They'll call back. If it's important. Oh, is that for you? Oh, okay. All right. You can go check out. All right. Yeah. So off to the side on my workbench, x squared plus x plus 1. That's your numerator. That's called your dividend. And then your denominator is x squared plus 1. That's your divisor. Now we did this back when we did limits. When you have multiple terms, you just look at the first terms first. How many times does x squared go into x squared? In other words, what's x squared divided by x squared? 1. You put it above there, and now you multiply from up top here. You distribute. That gives you x squared plus 1. And I went ahead and wrote the 1 underneath the like term. All right, the next step is very important. We subtract. So in this case, we're going to change signs. X squared minus x squared is 0. 1 minus 1 is 0. And this is really a 0 here. X plus 0 is just x. So you can bring down the x. Now, does x squared, you do it again, does x squared go into x? No. Okay, so it stops. This is our remainder. So we know that we can rewrite the integrand as the following. It's the quotient, 1, plus the remainder over the original divisor. Okay, this top part is called your quotient, and this is your d divisor. So it's going to equal the quotient plus the remainder over the divisor. And then dx. So what does that do? That splits it up into two terms. Let's see if we can handle each of them now. Can I handle the first term? What's the antiderivative of 1? Yep, that's x. Plus, let's see if we can do the next one. The next one, if I brought the denominator from the bottom to the top, it would be all to the negative first, right? Let's see if we can do it without rewriting it. That makes x squared plus 1 the inside function. What's the derivative of x squared plus 1? 2x. We get the x. We're only off by a 2. If we're off by a 2, we have to have a correction of 1/2. Now the rule of integration. When your inside function is in the bottom to the first or the top to the negative first, who comes to the rescue? The natural log of the absolute value of x squared plus 1, which we don't really need here because x squared plus 1 is positive, but we'll have it anyway. Safety first, right? Sleep with safety goggles, just in case. And there it is. All right, long division, and that's another AP strategy. So you'll have to know that. And again, this is easy to recognize because you'll have polynomial over polynomial. Completing the square didn't really seem like the thing to do here. So this one over here is even more disastrous, because this would be your inside function to the first. It's definitely not the natural log of that, because the derivative of the bottom is 2x. We're like way off, right? There's like 3 other terms up there that we don't get. But I'm noticing, hey, polynomial over polynomial, I got degree 3 over 2. Guess what I can do? Long division. So here we go. X cubed, the numerator goes down first, minus 3x squared, plus 4x minus 9. Now it is helpful, of course, to write it in descending order of degree. And if you're missing something, a placeholder, you can put a 0x or 0x squared if it's missing. Okay. And then on the outside, again, you write it in descending order. You don't really need a placeholder here. It's just helpful inside, because then you're going to have a column to put some stuff in. All right, now you start the process by just looking at the first dudes, right? How many times does x squared go into x cubed? In other words, what is x cubed divided by x squared? It's x, okay? A lot of people want to say 1, right? How many times is x squared into x cubed? Once? Well, that's not what we're really asking, right? We're asking what is x cubed divided by x squared? It's x. When you distribute now, x times x squared, you should get x cubed. That first column should be the same. If not, you did it wrong. And then plus 3x. Well, I'm going to write that over here underneath the x term. And now the critical point where we subtract. So minus, those go away. I bring down the negative 3x squared. 4x minus 3x is now plus x. And then I bring down the minus 9. So you could bring down the other things as well. And guess what? I try it again. How many times does x squared go into negative 3x squared? Well, that's the same as what's negative 3x squared divided by x squared. It's negative 3, okay? We did this when we found slant asymptotes back in the day, right? And now I distribute from up high here. We get negative 3x squared. Those are the same. And then we get minus 9. Write it under the 9, negative 9. And now I change both signs. So now they both become plus. And then both the first and last cancel, and we're just left with x. And does x squared go into x? No, we're done. So now I know I can rewrite this integral as parentheses, the quotient x minus 3 plus the remainder x over the original divisor x squared plus 3 dx. All right, and now the third term is really the most challenging of the 3, but it's really kind of what we just did, right? Let's integrate it now. I wouldn't integrate anything until you're ready to integrate every term, and make sure you have parentheses around it. So let's integrate. The antiderivative of x is 1/2 x squared. That's the derivative of x, right? It's x to the first. So add 1, you get 2, multiplied by the reciprocal. The antiderivative, or the integral of 3, is 3x. And then, of course, on the third one, it's kind of the same idea. It's on the bottom to the first. Its derivative is 2x. We're off by a 2. So I have a correction of 1/2, and it's in the bottom to the first. So it's the natural log of the absolute value. Safe to have it, not needed here though. Plus c. There you go. And you can imagine if it was x to the 4th over x cubed or something like that, you just have more terms. So long division. That's about the extent of both of them. It turns into something we recognize, but it's a strategy. It helps us put it algebraically into a different but equivalent form that we can manage, just like completing the square, just like splitting up terms in the numerator. Whew. Lots of strategies. You know what? We're not going to finish today, and that's okay, because tomorrow is March 1st, and we'll finish tomorrow. Yeah, I did the long division off to the side of my workbench. When you can, you try not to interrupt the flow of the problem. The only time I do that is when it's an inverse trig, just because I like to see it right there. It's not the best practice. I would probably take off points for myself, but it's easy. So we're going to try and test Friday. Did I say that at the beginning? Did you see that at the beginning? I wrote that. That's still a few days off, but I want to test 4-1 to 4-4 on Friday. It's an even day. It's a good way to end the week, right? So, and those are huge sections, 4-3 and 4-4. So we'll have 5 more questions tomorrow, and maybe 5 questions on Thursday to get you ready for Friday. The worksheets are out there. Have them all done for what you want credit for by the end of the 9 weeks, because that's when I'll go in and look at them. You want to be here Friday? Okay. When we free 80, is that okay? Just free 80, free 75? Yeah. Yeah. We'll take it. We'll talk. You can take it before or after Monday morning or Monday. Yeah, no worries. I don't think y'all are gonna go out and solicit answers.